Chapter 5, Discrete Random Variables. First is Section 1 is mostly vocabulary. We need to first identify what a discrete random variable is. And what a discrete random variable is it's a quantitative variable whose value depends on chance. Now remember that quantitative means that it's something that's numeric. A discrete random variable is a random variable whose values can be listed. That's where the discrete comes in. And now for notation, when we are doing notation for random variables, we use capital letters. So for example, I'm going to let capital X right now represent the number of siblings. So when I have this notation right here, that would represent the number of having exactly 3 siblings. This notation right here with the P out in front represents the probability of having exactly 3 siblings. And a probability distribution is a list of your possible values for your discrete random variable and their corresponding probabilities. Normally it's going to be in a table. So in the left column you'll have a lowercase x in this case, since I decided my random variable was x, and that would represent having 0 siblings, 1 sibling, 2 sibling, 3, and so on. So this is the specific values that our discrete random variable can take. And then our right-hand column would be the probability that capital X equals lowercase x. So in this blank right here would be the probability of having exactly 0 siblings, and then the probability of having 1 sibling and having 2 siblings. One thing to keep in mind is the sum of your probabilities is going to be equal to 1. And our last vocab word here, a probability histogram. It's a histogram of our distribution here. So you would take this table and you would change it into a histogram. So we're going to look at page 213, example 5.2. Now if you read through this one, it is a number of siblings, and it refers you back to example 5.1, where they give us a frequency table. They want us to determine the probability distribution of the random variable x. So we are going to go ahead and set up our table. We're going to have x and then the probability that capital X is equal to lowercase x. And according to the frequency table on page 212, the number of siblings is 0, 1, 2, 3, and 4. Now we have to calculate our probability of having each of these. Well, you can do it using the frequency column that they gave you on page 212, or you could actually do it using the relative frequency, because the relative frequency is actually our probability. So our probability of having 0 siblings is going to be 8 out of 40, because there's 8 people that had 0 siblings and 40 of them that they surveyed. That ends up being 0.2. Probability of having 1 sibling would be 17 out of 40, which ends up being 0.425. Probability of 2 siblings would be 11 out of 40, and that would be 0.275. And the probability of 3 siblings is 3 out of 40, so that's 0.075. And the probability of 4 siblings is 1 out of 40. That's 0.025. So that right there would be our probability distribution. Second part, they want you to construct a probability histogram of our random variable x. If you turn to page 214, they have a very nicely drawn histogram. I'm not even going to attempt to draw it here. They basically show you across the bottom is your number of siblings, and then each bar goes up to the corresponding probabilities. Okay, if you go to page 215, example 5.4, this is dealing with a coin toss. So go ahead and read that one. And then Part A says use random variable notation to represent the event that exactly 2 heads are tossed. Well, from your problem, it tells us to let x denote the total number of heads. So for this particular one, x represents the number of heads. Well, Part A wants us to use random variable notation to represent the event that exactly 2 heads are tossed. So what they're looking for part A is simply x equals 2. Okay, part B, they want you to determine the probability that x equals 2. So now we're actually looking at our probability. Well, if you look at the table 5.5 on the bottom of page 215, you can see that there's a total of 8 outcomes when you flip these coins. And the number of outcomes that have exactly 2 heads is 3. So we actually have a 3 out of 8 for our probability, which would also be written as 0.0375. So that would be part B. Part C wants us to find the probability distribution of x. So this time they're wanting us to find the table. So we would set up x on the left-hand column and then probability that x equals x in the right-hand column. Now remember, we're dealing with the number of heads when we toss this dime. So we could have 0 heads, 1 head, 2 head, or all 3 heads. And from our table on page 215, that table 5.5, we can get 0 heads only one way. So I'm going to have 1 out of 8 ways. I'm not going to fit the decimals on there very good. One out of 8 ways to get 0 heads. Now the number of different ways that we can get exactly 1 head is 3. It could come first, it could come second, or it could come last. So we're going to have 3 out of 8 ways, which is equal to 0.375. Now when you're doing your probability distribution, you actually only need the decimal portion of it. You don't have to have the fraction, but I'm just showing you where these decimals came from. It's why I'm including them. And then 2. There's exactly 3 ways that we can get 2 heads. So that's going to give us 0.0375 again. And there is only 1 way to get exactly 3 heads. So that would be our probability distribution. Part D on page 216 says use random variable notation to represent the event that at most 2 heads are tossed. Now remember, at most means we want 2 or fewer. So for part D, we would like to know the probability. Oh nope, we're not doing probability. We just want the event. So we want the fact that x is less than or equal to 2. So that would be part D. Part E is where they want us to find the probability. Well, from my probability distribution that we did in part B, I can find my probability of being 2 or less by adding my probability of getting 0, 1, or 2. When I add all those up, I end up getting 0.875. So part E is 0.875. Okay, another thing to consider is that when you're actually doing a real experiment, your probability distribution or your histogram may not match exactly the theoretical, and the theoretical probability is what we calculate. It's what should happen. But the more observations that you do in your experiment, so the more times you perform your experiment, the better your approximation should be. They give you an example of this on page 221 in your book, where they have done a simulation. It's down towards the bottom, figure 5.3, and they show you how after you do a lot of observations of it, you actually come closer to that red dotted line, which is the theoretical probability. So the more observations that you do, the better off your experiment is going to represent your theoretical probability.